Hello, good afternoon. My name is Alan, and this will probably take 30 of lesson 4, where I'm trying desperately to get going on this debugging program demonstration, where we're going to look at the 8086 16-bit processor. We can't actually look at a real one. That would probably be something you find in a museum, but we can simulate one using a special program called debug. Now, I'm going to make a special directory for us to do our work and run the program. And I'm not going to explain too much, except to say that most of the stuff you can figure out on your own. Okay. This program gives us a view of the 8086 16-bit processor. One view, one way to look at it is to look at the CPU's registers, and here they are. If you count it up, you'll notice there are 13 registers, each with different names and different meanings. I will go through the meanings as they come up. There's a hidden register you can't see, and that is called the flags register, and it is represented here by these funny little symbols. One thing I want to do right now, though, as it was part of my demonstration, my last try, is if you notice here, see if I type D, which means dump memory, this memory here is filled up with a special magic value, which has a meaning which I want to explain when we get to it. So I'm going to clear all that out. I'm going to fill all that memory up. From zeros. And it's all zeros now. Okay. I wish I could clear the screen. Maybe I can. Yeah, it's still zero on there. Okay. The register. The registers are the immediate memory that the processor works with. This memory, that is dumped here, is not immediately accessible to the processor. This has to be fetched either from RAM, random access memory, or it could be from a disk drive, or it could be over a network or from the internet, or some process that takes a long time. But this memory is right in front, hardwired straight into the processor, and it can use it right away. Now, I was trying to remember and trying to think up some examples of commands, Intel instructions, I should say, for this processor that find interesting. Well, maybe not the commands themselves, but the way that they behave. And I was trying to remember what the command was for divide by. I want to divide 5 by 6 or something. What was the command? I tried entering things in, like if you want to enter a command, you type A, and then it gives you this prompt. And if you can remember the command, you can type it in. So I tried first div, and then I tried cx, 2, and it accepted it. So, okay, that sounds like it's going to divide cx by 2. So I want to change the value of cx, which is done this way. Parse register cx, change to, well, make it 4, let's say. And let's look at registers again. And let's run this special command. And it's still 4. Now, why is that? And look at the command. There's no 2 here that I typed in. Why is that? So, this is unusual. I still haven't figured out why it allowed me to put a 2 here. But, eventually I did figure it out. What it is you put the number you want to divide by into AX. So I'll say RAX 5, let's say. And the numbers that I want to divide the AX register value by, I put into the parameter of the div instruction. And in fact, I didn't want 4, I wanted 2. Let me change that to 2. Alright. Now, what I was curious about is, since 2 doesn't go into 5 evenly, where does the remainder go? And I suspected, I think it goes into dx. Okay? Well, that's my theory. So I'm going to run, oh geez, I can't run my command because I'm not at the right spot. Notice this is not saying div cx. Now, what I've got to do is somehow get back to 100. I got to change this value, the instruction pointer to point here. So I can do that. Like anything else. Change that to 100. Alright, we're ready to go. I'll trace through the instruction. Well, as expected, 5 divided by 2 is 2, and the remainder, 1, in fact, went into dx. So that's pretty good. Alright. Alright, well, what happens if I run it again? So what I did was, I've got a junk instruction here that's just garbled nonsense. So what I put here is a jump back to 100. See how easy assembler is? Okay, so this is now going to jump back to 100. And now it's going to divide again. Now what I expected to happen would be that this 2 would become 1, and this would become a 0, and that would be the end of the story. But watch what really happens. Well, indeed I got a 1 here, and this did become 0. But look at this. There's an 8 here. What's this 8 doing here? So I thought, well, let's just keep, this is a loop, so let's just keep looping through and see what happens. And if you notice here, there's a kind of cycle going on as I trace through. I'm hitting enter twice. Alright, and now I'm back to where I began, 5 and 2. There's the 1. And I'll do it again. And there's 8 again. In fact, it's going in a big circle. To speed things up, what I did was I looked over here. This shows me what they call the off code, instruction code for this instruction, F7, F1. So instead of jumping back, jumping, I decided to just fill up all memory with divide by CX. So I used the fill command from 100 to 1000 with F7, F1. See, it's all the same. And now I don't have to jump back anywhere. It's always now divide. Now I can trace through much quicker. And you'll notice the cycle repeats over and over and over again. Now, I'm the kind of person that can't remember anything, so I've got to figure everything out from scratch every time. But I had a hunch that 8 that's going to appear after this instruction is because this 1 is going to move itself to the top of this AX register, and that gives me an 8. Why is that? Well, let's just have a look. I'm going to put over here to my scratch pad. I'm going to put DX on the left. In binary, alright, and I'm going to put AX. Put label right here, but I want to line it up this way. It's easier to read. AX is 2. Yes. Oh. So that's 2. And it says 1. Alright. My theory holds true. When I divide by 2, which is the same as shifting things to the right by 1 position, this 1 here is going to drop off of here, fall down here, and it's gone. And this will become 0. And this one will shift over by 1. And the answer will be AX is 1000, which is 8. And 2 zeros, 1. Well, we've actually seen it happen about 100,000 times. We'll trace through it. There you go. See? And dividing by 2 keeps shifting things down and down and down. So, what's going to happen on the next division by 2? Well, my guess would be that since 1 doesn't divide evenly into 2, there should be a remainder, and we should get another 1 over here. And then this should become a 4. Let's see if this theory is true. This theory is true. We divided by 2 again. This went here. This disappeared. That's not 8 anymore, that's 4. And the remainder became 1. So I'm not keeping up to date for these. Well, that's quite interesting. It says something. Alright. For one thing, it tells me that if I do another division, this remainder here is going to get tacked on to this 4. So if I divide again, what I expect to happen is divide 1, hello new 1, you go down 1, everything else is the same, and that's 8 plus 2, which is 10, or 3 in x, and the result should be A000. See? There it is. So now I figured out the div instruction. Sort of. The question is, why does it work that way? Why is it taking that remainder and popping it over back on top again? Then, maybe I can either leave that question for you to answer, or maybe I should just tell you the answer. And the answer is the following. The div instruction is actually a 32-bit division of dx. So div. Now this is just what I figured out by playing, not from a book or anything. Div instruction. Div, and then register value, not including dx or ax. So we can use cx, maybe bx. Let's say cx divides the value dx ax by cx, and the remainder goes into dx. Okay, now that's a 32-bit number. So let's think of a 32-bit number. Well, we might know the answer. Good. Wow. How about this number? That's a great big number. 4 billion. More than 4 billion. And suppose I divide that by 10. What should happen is this should become 0. These remain the same. And then the remainder is supposed to go into dx. But how can the remainder go into dx? Dx is not empty. And that's when I realized what was causing this problem. RAX RDX 2. Okay. Now let's try and do this division. We crashed the system. The system crashed. And the reason is after the division, dx wasn't 0, and so there was no place to store the remainder. And that's called a divide overflow error. So now you've learned about a new processor exception. And I guess I'll leave it there for now, and we'll go on to other things next time. Thank you.